Imagine a city where every road needs monitoring. You do not want to place a camera on every single intersection because that would waste money, maintenance effort, and network bandwidth. Instead, you want the smallest set of intersections so that every road touches at least one chosen point. That simple-sounding question is the heart of the vertex cover problem. In this video we will build the idea from intuition, turn the city map into a graph, walk through a greedy strategy, and understand why the method is fast even though the exact optimal answer is hard to compute. A graph is just a clean mathematical model for relationships. Vertices represent objects, places, or decision points. Edges represent links, roads, cables, or dependencies between those vertices. Once we think in this language, many real systems become much easier to reason about. For vertex cover, the rule is very specific. We must choose some vertices so that every edge has at least one endpoint inside the chosen set. In the highlighted example, the green vertices touch every connection, so they form a valid cover. It may not be the smallest possible cover, but it satisfies the definition, and that distinction matters a lot. Now let us sharpen the problem statement. We are not looking for just any cover. We want the minimum vertex cover, meaning the smallest valid set of vertices that still touches every edge. That optimization target makes the problem difficult. In theoretical computer science, minimum vertex cover is a classic NP-hard problem. That does not mean it is impossible to solve on small graphs, but it does mean we should not expect a fast exact method for every large input. So in practice, approximation algorithms become valuable. They trade exact optimality for speed, simplicity, and predictable quality. The greedy intuition is easy to remember. If a vertex touches many uncovered edges, selecting it gives a large immediate payoff. So at each step we choose a vertex with maximum degree among the remaining graph, place it into the cover, and delete all edges that are now covered by that choice. Then we repeat. Greedy algorithms make locally attractive decisions and hope those choices add up to a strong global result. Here, that strategy does not always give the perfect minimum cover, but it usually gives a useful answer quickly, which is exactly why it is common in interviews, teaching, and large-scale systems. This walkthrough is the heart of the video, so let us go slowly. Each number on the right shows the current degree of a vertex, meaning how many uncovered edges still touch it. At the beginning, vertices A and C are tied for the highest degree. A greedy algorithm is allowed to break ties arbitrarily, so we will choose C first. That single choice is attractive because C touches the center of the graph and immediately covers several edges at once. After selecting C, every edge incident to C disappears from consideration. That is the crucial shrinking step. Greedy is not just picking vertices. It is repeatedly solving a smaller and smaller version of the same problem. Now A has the highest remaining degree, so A becomes the next natural choice. Notice how the degree table changes after each removal. Those updates tell us which part of the graph still carries the most uncovered structure. Once A is added, most of the graph is already handled. At this point, only one uncovered edge remains between E and F. Either endpoint would work, because picking either one would touch that final edge. This is a nice example of how greedy decisions often become very simple near the end. The graph has been reduced enough that the final move is obvious. The final greedy cover is the set A, C, and E. Is that guaranteed to be the minimum possible cover for this graph? Not always. But it is valid, it was obtained quickly, and each decision was guided by a very local rule that is easy to compute. That combination of speed, simplicity, and reliability is why greedy approximation is so useful in practice. When an exact algorithm is too expensive, a method like this gives us a high-quality answer without waiting forever. Why not just search for the perfect cover directly? Because the exact search space grows explosively. A brute force approach would need to examine subsets of vertices, and there are 2 to the v such subsets. That becomes infeasible very quickly. The greedy version is much lighter. A straightforward implementation can recompute degrees and run in roughly O of v squared plus e. With stronger data structures such as a priority queue, degree selection can often be handled more efficiently. The exact bound depends on how updates are maintained, but the practical takeaway is simple: approximation buys speed. Approximation guarantees are what make this algorithm intellectually satisfying. Even though we are not promising perfection, we are also not flying blind. For the standard approximation approach to vertex cover, the result can be bounded within a factor of 2 of the optimum. In plain language, that means the solution size will never be more than twice the size of an ideal minimum cover. That worst-case bound is powerful because it gives us a safety guarantee before we even see the input graph. The proof idea compares the algorithm's decisions against what any optimal solution must also be forced to cover. Vertex cover appears whenever we want a small set of control points that collectively touch every relationship. In network security, that might mean choosing a small number of monitoring devices that can observe every critical connection. In biology, it can model selecting a compact set of genes or proteins that cover important interaction pairs. In scheduling and dependency analysis, it helps identify small checkpoints that intersect all key constraints. And in wireless or infrastructure planning, it provides a first approximation for where limited resources should be placed. The abstraction is mathematical, but the motivation is often deeply practical. Let us bring everything together. A vertex cover is a set of vertices that touches every edge. Finding the smallest such set exactly is difficult, which is why approximation algorithms matter. The greedy strategy focuses on the highest degree remaining vertex, covers many edges at once, and keeps shrinking the graph until nothing is left uncovered. The result is not guaranteed to be perfect, but it is fast, understandable, and often strong enough for real decision-making. That is the broader lesson here. In algorithm design, a well-structured approximation can be far more useful than a perfect answer that arrives too late. So whenever you meet a hard optimization problem, remember this pattern. First understand the exact objective. Then ask whether an approximate answer with a clear guarantee might be the better engineering choice. Vertex cover is one of the best examples of that mindset. It connects theory, visualization, and practical decision-making in a very elegant way. Thank you for watching.